Now we're starting chapter 7. Chapter 7 deals with integrals and transcendental functions. Probably the first time you ever heard the word transcendental. All that means, transcendental functions, besides the trigonometric functions, the hyperbolic functions, and the inverse functions, transcendental functions include e and pi. So those kind of functions, the trigonometric functions, the functions with respect to e, logarithms, those are all transcendental functions. The thing about logarithms, what is the formula for a logarithm from algebra? What does a logarithm look like? How many different types are there? There are 3 forms of logarithms. The logarithms look like this. Look like this. It's red. Log base A of x equals y. That's how it's read. And it all depends on what the base is that defines the type of logarithm it is. If we have a base of 10, since our numeric system is a base 10 numeric system, we go from 0 to 9, 10 to 19, 20 to 29, 30 to 39. We'll go in series of 10 numbers. So we're base 10 in our counting system. So if you have a log base 10, you would represent it like that. If you don't see a base there, it's automatically a 10. This is called a common log because it's of our numeric system. Undoubtedly, you all heard of the letter E, the number E. It's a constant. If we have our base of E, which is 2.718178, I forget what it was. It's some constant number. If we have a log base E of x, then we would write it this way. We call that a natural log. And then then anything else would be written as log base a of x equals y. Any other number other than 10 or e, you just leave it as it is. How are logs and exponential functions related? How are logarithmic and then exponential functions related? What is an exponential function? Yes, but what does it look like? What does the function look like? We know logarithmic equations are log base a of x. Exponential functions, e to the power x. Or that's one, it's general a to the power x. And so we had this. The natural log of y is equal to x. It's log base e of y equals x. The way you convert logarithms to exponential equations is the base stops being the base of the logarithm and moves over here is now the base of the solution. So e to the power x is equal to y. Logarithms and exponential functions are inverses of each other. Remember, normally we would have started off as ln x equals y. But how do you find the inverse? You switch x and y and solve for y. So logarithms and exponential functions are inverses of each other. In other words, they cancel each other out. The property of inverse functions that if you take a composite functions of a function and its inverse, the answer should be x. And in calculus, as you've seen, most of the times we only use ln x because it's easy to write. The definition of the natural log function. Remember, what does natural log look like? So the definition is this. The natural logarithmic or natural log is the function given by the equation ln x is equal to the integral of 1 to x of 1 over x dx. And x logarithms cannot have a negative value. So the x has to be a positive number. So what's wrong with this? X is being used in too many places, too many times. So it has different meanings. So that's what we have to do. We have to try to redefine what our value, not of x, because that's the input, our bounds. What would we get if we had this equation? ln1. Why? That's straight memory. You memorize ln1 that's the x-intercept. But how do you do it from here? Right. Yes. Because if you're going from the beginning to the end of the same numbers, you're right. You're just going to be subtracting the same values, which will be 0. That's the reason it's 0. So what we have to do here is we have to define our ln x from 1 to some value a. Or you can use t. It doesn't matter what you use there. What about if we use e? What is e? The number e is a number in the domain of the natural 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 logarithm ln e from 1 to e So what is that going to equal? What does that equal? You would think. No. algebraically, we know what this one is because we know that log base e, that's what ln is, of e is equal to x, some number x, right? Ln means log base e of e. So let's convert this to exponentials. This comes over here, so we have e to the power x. The log falls away. So for e to the x to equal e, what does x have to equal? Yeah, because that's the exponent is 1. So this function equals 1. So that integral of 1 over t, whatever that, because we're not going to use x because we're using e and x. So let's go ahead for giggles and grin. Let's go ahead and take this integral. How would you do it? Take the integral of 1 over t dt, or 1 over x, whatever you want to use. We would rewrite this equation as t to the power -1. And the rules for integration is what? Take the top of your exponent and do what with it? So we have -1 plus 1. And on the bottom, we'd have -1 plus 1 from 1 to e. Retro. You see why this is a problem? Because what happens on the bottom? We can't have that. And it's not 0 over 0 either. So that's it's a transcendental function. Whenever we see the integral of 1 over x, let's see, I'll use back to x like running x. That's why we say the integral of 1 over x is ln x through its domain. Because there's also another way. Since this doesn't work, we're going to look at another way. The derivative. Let's look at, because integrals, when you take the integral of something, you're taking the integral of the first derivative. Remember? So the integral of f prime of x dx is equal to the original function from a to b. So let's look at the derivative of y equals ln x. So the derivative of ln x dx So this, remember, from up here, this is the same as saying the derivative with respect to x of our integral from 1 to x, 1 over, 1 over t dt is equal to 1 over x. So the derivative of the formula is this: the derivative of ln x dx is equal to 1 over x. But that's pretty limiting. Can you take a limit? Does it always have to be of x, or can it be a function? Well, as long as it's a function of x, yes. So basically, we can take the limits of some function of x. Or not the limit, but the natural log. Well, instead of putting fx, that looks very weird. What we're saying, we're using substitution. We're saying that u is equal to f of x, is our function. So what we're saying here is now we have ln of u. So the derivative of ln u with respect to x remember, we have to do it in two parts because we have to take a derivative of the ln, and then we have to take the derivative of the function. So what's the derivative of ln? 1 over whatever this is. So it's 1 over u times the derivative of that, which is du dx. And that's going to be, so it equals du over u. The For any general natural log, the derivative of the log is the derivative of the function over the whole thing. Is there a limit? Is there a restriction on the domain of this function? Because up here, when we take the derivative of ln, we know that x has to be strictly greater than 0 because you can't take the ln of a negative number. Remember the graphs of logarithms? What you said, it crosses through 1. You cannot have a negative logarithm of a negative number. So our domain has to be strictly greater than 0. So then here, our u has to be strictly greater than 0. How can we fix that? Well, what if we take the ln of an absolute value? If we took the derivative of ln of absolute value of x, what would that equal? What's the derivative of ln x? 1 over x. But since x is absolute value, all we can do is saying that it can't be 0. Because since x can be positive or negative or anything except 0, That's the only restriction we have. If you take the ln of the absolute value, the only restriction we have is the bottom can't be 0. Well, what if we had a coefficient inside there? The restriction here is this product has to be greater than 0. What's the derivative? One over bx times what? The derivative, yeah, is the derivative of bx, which is 1 over bx. The derivative of, as you said, who said that? The derivative of bx would be b. The b's cancel, so we're back down to b 1 over x. And the graph of ln x, so there's the graph of ln x. Funny enough, it looks like the graph of any other ln, where the function itself is equal to 0 at 1. What's the inverse of ln x? If we drew a 45-degree angle line right here, the inverse would be a mirror image. So this is ln x. Which function looks like this? Mhm. Let's go back in time to review our properties, or some of the basic properties of natural logs. Here's one of the reasons why, remember when we took the ln of bx and took a derivative? The derivative of is 1 over x. Here's the reason why. Here's one of the reasons why. Whenever you have a product, you can split them up and add them together. Remember, b is a constant. So this is a value, it's a number, ln x. So if I take the derivative of this, then I'm taking the derivative of both of these separately. What's the derivative of a constant? 0. And the derivative of ln x? 1 over x. So that's how we got 1 over x. It'll always be the case. One over ln of b over x. Since multiplication makes things bigger, that's why we add them. Division makes things smaller, that's why we subtract them. So with this logic, what would the derivative of ln b over x be? Negative 1 over x, yeah. D of ln b over dx minus d over ln x dx. The derivative of a constant is 0 over 1 over x. Another property. There are two ways you can prove this one. The first way, we can prove it the way we just did. What's the ln of 1? 0. Because in our graph, when x is 1, y is 0. So that one's 0. So we have negative ln x. Or we can rewrite this one, bring the x up on top, and the exponent is negative 1. In logarithmic equations, if you have an exponent, it can come out in front. So either of those methods work. And again, it also helps you when you take the derivatives of these things. And 4, oh, no, r, because r is going to be rational. So ln of x to the power r, where r is rational. Again, any exponent comes out in front, where r is rational. the integral of 1 over u du. If you take the integral of 1 over u du, that's and from what we've been doing, what does that come from? What if this is the derivative of something, where did it come from? Because think of it, we took the derivative of ln u, what do we get? Du. So we have du over 1 over u du. So when we take the integral, we go back to where it came from. So now we're just working backwards. Again, we're dealing with inverses, the opposites of each other. Here's example 1. So what does this really mean? What this really means is this. Du is a derivative of u, right? And we said that u was a function. So what du over u represents is the derivative over the function itself. Which is, because it's of this case, du over u, then we know it's the example here. Let's do an example. Example 1. Negative pi over 2 to pi over 2. So what do you think? Does this match our form du over u? So let's check. If we're seeing if it matches du over u. So if our u was 3 plus 2 sine theta, what would du be? 2 cosine theta. So we're pretty close. What are we missing? What are we missing for here to make this multiply by 2? So what we have is if we multiply by 2, then we have 4 cosine theta. So our equation matches two du over u. The 2 is a constant, so it goes out in front. So we have integral of du over u. What is the integral of du over u? To our bounds. We have ln of pi over 2 minus ln of negative pi over 2. Well, it's at u pi over 2. It's because u is this function. So we're taking 2 ln of 3 plus 2 sine pi over 2 minus ln 3 plus 2 sine negative pi over 2. What is sine pi over 2? One. So that's 1. So we have 3 plus 2, so we have ln of 5. The sine of negative pi over 2. Yeah, because negative pi over 2 is down here, so it's negative 1. So this is negative 1. So we have 3, 2 times negative 1 is minus 2. Ln 5 minus ln 1. Natural log of 1 is 0. So our final answer is 2 times ln 5. And that's our answer. So yeah, once you notice or it can manipulate it so it matches the du over u as an integral, then we know that's a natural log. The inverse of our natural log and the number e. If we were to draw these graphs, what would they look like? This is e to the power x. This is ln x. If we take the ln and the limit of the inverse of x as x goes to infinity, what would we get? What is the inverse of ln? Mm-hmm. So as x goes to infinity, where does the value go? Because yes, this is e. So e to the power x. What if we went the other direction to negative infinity? Where's that one going to go? Yep. Because as we're going this way, if we're going to negative infinity, we're going to zero. So we figured we saw earlier how to find the inverse of ln x. So the inverse of ln x is e to the power x. So let's look at e to the power x, or e. Let's look at the properties of e. What does e squared mean? Yeah, e times e, which is the constant times the constant, right? How about square root of e? How can you rewrite that? How about if I gave you this? The root always goes on the bottom and the exponent goes on top. The root goes on the bottom and the exponent goes on top. What if I had a negative exponent? So why would you know this? Because you can rewrite your function to make it easier for you. As we saw with the properties of the ln's, we can rewrite those to make them look much easier for us. What does ln e equal? Does everybody see why it equals 1? Log base e of e equals x. We just went this earlier. So to convert it to exponentials, we have e to the power x equals e. The log drops off. And the only way they can be equal is if x equals 1. So it equals 1. And the properties. Ln e to the power n is n ln e, which is just n. Let's look at the definition. The definition of a natural exponential function. For every x, we can define a natural exponential function as e to the power x, and we could write it as what is this first one equal? Hmm? Oh, okay. It equals x, yes. Why? How do we prove that? That proves it for one number. Let's look at this thing as an answer. So we're saying that e ln x is equal to e log base e of x. We're saying that equals some number x. What if we take the ln of both sides? That means now ln x is out in front, because remember, exponents go in front. Ln e we know is 1, so we have ln x equals ln x. So for any value x, it's going to be true. So for the only way this is true is if x equals x. How about this other side? What is that going to equal? Also x. Aren't these compound functions? A function within a function? A function within a function? Yeah. And by definition, an inverse function is proven by taking the compound function f of g of x, or this equals g of f of x, which it always equals x, which is what we just proved. This is an algebraic property. So if our f was ln x, and our g was e to the power x. What this one says is, so it's ln of e to the power x, or e to the power ln x, and the only way that could be true is if they both equal x. We know that ln and e are inverses of each other. Is ln differentiable on its domain? Is ln differentiable for all x is greater than 0? Yes, on a domain, because it's a continuous function. Because it is differentiable, its inverse is also differentiable. Since ln x is a continuous function on its domain, then so is its inverse. Therefore, well, inverse on its range. Therefore, they are both differentiable. Remember what I said earlier, if it's continuous, it's differentiable. So we're looking at E. Let's look at its derivative and integral. And the beautiful thing about E is its simplicity. Let's say f equals ln x. We're saying that y is equal to the exponential function. This exponential function is the inverse of the logarithmic function. Since ln the inverse, that means it's the inverse of the function. So let's look at this. If this is all true, then this has to be true. Then dy dx has to be true. Remember, we're looking for e to the x. So the derivative of e to the power x, if all this stuff is up here, is true, then we can take the derivative of the ln inverse of x, which means we can also take the derivative of the inverse of the function of x with respect to x. Now, what this one equals, it is 1 over f we did that earlier in chapter 5, remember? So we have 1 over f prime. The f inverse is equal to e to the power x. F inverse, which is inside there from chapter 5, is e to the power x. Oh, yeah. Then if take the derivative of this, it'll give you a negative exponent. So the derivative of e to the power x is e to the power x. F F inverse f prime e to the power x. Yeah, because the derivative of our original function is an ln, which is 1 over x. So the derivative of our original function is the derivative, or du over u. This is u. The derivative of e to the x, eu, is 1 over e to the power x. So it's 1 over e to the power x, which is e to the power x. So that proves the derivative of e to the power x is e to the power x. That's why I love e to the power x. Again, the exponent could be a function as well. We can the exponent of our e could be a function of x. When that happens, we take the derivative du with respect to x times e of u. So if we had e to the power 3x squared plus 2x, the derivative would be the derivative of this 6x plus 2 times e to the 3x squared plus 2x. In other words, when you start off with e, you always have to end up with the exact same e. So again, if it's differentiable, the limits have to exist. As x goes to negative infinity, as x goes to positive infinity, what do we get? If it's differentiable, we have to be able to take a limit. Right. Because of the graph, it looks like this. Here's the beauty of the EU function. Since the derivative of EU equals EU du, the integral of EU du is equal to the EU plus C. Again, ln's pretty, once you get used to it, they're pretty straightforward. It's whatever the exponent is, or whatever the ln function is that goes on the bottom, and the derivative of it goes on top. But EU is much easier. As long as you have the derivative of the exponent, if you're missing anything, just plug it in there. The laws of exponents. E to the power x, or e to the power n even, doesn't matter. From algebra, when you're multiplying the same bases, you add the exponents. When you're dividing the same bases, you subtract the exponents. If you have an exponent to an exponent, you multiply the exponents. Anything to the 0 power is 1. Well, for this top one, it's n is larger than m. The exponents. If m is larger than n, then you subtract on the bottom. In other words, if I had e to the 5 over e to the 7, I could use rule 2 and subtract the top minus the bottom. This would give me e to the power -2. Or I could do rule 5. 7 minus 5, which is 1 over e squared. These are both equal. E to the power -2 is equal to 1 over e squared. So a negative exponent simply means change the location of it. These are the same exponential rules as we had in basic algebra. And it doesn't have to be e, or it could be any base a. All these rules apply to any base a. The derivative of a to the power x a is a constant. Because I'm trying to remember how the best way to prove it. It's going to equal x ln a. The derivative of any base a to the power x is equal to x to the power e to the power x ln a. Because a is the same thing as e ln a. True. So if we have a to the power x and we have e ln a to the power x, then power to a power you multiply. So we have e to the x ln a. Yeah, right, there you go. Because a, that's true. That's a given. Yeah. So the derivative of this is that because x goes to 1 when you take the derivative of it. No, let's see if we go again further. We just rewrote ax as that. So the derivative of e to the power x ln a. So our u is x ln a. So du would be ln a. So the derivative of e to that would be ln a e to the power x ln a plus c. But e to the power x ln a from up here is ln a to the power x. So we have a to the power x times ln a. That is the general derivative. Which on my next example. Oh, okay. So that's the derivative of any base a to the power x. How about if we integrate it? Integral of a to the. So if we integrate a to the power x dx, remember our derivative is ax ln a. We have to know this. If we're going to take the integral, what do we need? We have a to the x. What do we need? Ln a. That's a constant, isn't it? So we would need 1 over ln a integral ln a to the power x dx. Because the integral of this is a to the power x. So there's our rule for integration for that. No, plus c, forgot. This is indefinite integral. Let's go jump in this one. Oh no, we got to first talk about logs base a. So far we talked about logarithms base e. We need to talk about log base a. In other words, any other base. We have to talk about that. Yeah, that's what we're going to talk about. So if y equals log base a of x, that means a to the power y equals x. And if I take the ln of both sides, then I have y ln a is equal to the natural log of x. Y equals natural log of, which is the change of base formula. All right, so the derivative of that one works. Everybody remember the change of base formula? Because, okay, first, why do we need to know the change of base formula? Is because our calculators only calculate on base 10 or base E. If you look at your keys, you either have ln or log. There's no key on your calculators that say log base A. So if you have a log base 3 of X, what you would do is rewrite it as that. Because your calculators has an ln function, and this is a constant, and this is whatever value you want to put in there. So whatever your base is goes on the bottom, whatever your function is goes up on top. That's the change of base formula. What if we had this? How can you rewrite that to make it easier? Nope. Then we're stuck with XY. You can't take an XY. Good try though. Do we know any other rules? How can we rewrite the top function? Mhm. Because now we can split them up. Because now this function here is actually log base A of X plus log base A of Y. You have to, because of the restrictions of what your calculators can do and cannot do, we have to know how to transform the equations so that our calculators are function are useful. And these rules would help us. Now we've talked about logarithms, natural logs, taking derivatives and integrals. Let's see what we can do with these guys. In other words, let's look at derivatives first. So if I took the derivative of log base A of X with respect to X, what would be my first logical step? Remember, our calculators cannot do log base A. So what do we do first? Very good. Then what? Because remember, it's a derivative of this function. The only one that has an x that I think we can differentiate is that one. So what does that become? So we have 1 over ln a times 1 over x. So the answer is 1 over x ln a. Okay, now we can do the examples. I was trying to get to these. This section only had 2 examples. I'm sorry. It's a very boring section. And I do apologize. I could have just shortened it into about half hours, saying that okay, let's take the derivative integrals of ln, log, and e and a. It's only 4 functions, and I just showed you here the rules. All right, my first example question. There's find the derivative of log base 10 of 3x plus 1. Go. Oh. Actually, before we do this one, let me show you. I do apologize because I know we just did one on um, log base a of x. Let's look at this example of log base a of a function. Let's take the derivative of log base a of a function. The derivative of some function. So the first thing we have to do is rewrite this as the fraction. So this becomes ln u over ln a. The ln a is a constant, so it can go out in front. What's the derivative of ln u? One over u du. The du with respect to x. So this is the shortcut answer. When you have the derivative of a log base a of u, the answer is 1 over ln a, 1 over u times du with respect to x. This is the shortcut. So in our example, I just gave you, let's label these things. This is a, this is u. So what is du? So let's just plug them in there now. 1 over ln 10, 1 over 3x plus 1 times 3. And there's your answer. So there's no reason going through all the other stuff. It's just label a, label u, take the derivative of u, and just plug them in. Let's do another one like that. Log base 7 of sine x. This equals y. Find y prime. Remember, it should only take you 4 steps. Well, actually, 1. This is our a. This is our u. So what's du? So the answer is 1 over ln a, 1 over u du. Ln 7, 1 over u. Yeah. Sine x. On top, it's cosine x. Let's try an integral one. The integral of log base 2 of x over x dx. Yes. So we have to do the same thing we've been doing in the past. So this top part becomes ln x over ln 2 divided by x over 1. So that's ln x over ln 2 times the flip of the bottom, dx. ln 2 is a constant, so we can bring it out in front. 1 over ln 2. ln x over x dx. Integral of ln x over x. So let's say that u is ln x. What's du? 1 over x. So u du would be ln x over x. So this is actually the integral of u du, according to all this. U du is add 1 to the exponent, so it's u over 2 u squared over 2 ln 2 plus c. So u squared over 2, u was ln x. So we have ln x squared over 2 ln 2 plus c. I'm not going to lie. The hardest part is noticing what your, because this should always be a function of u du or 1 over u du over u. That's the hardest part. You have to keep on looking for it till you find that value. Yeah, because getting here is easy. And then when you convert to a function to u, always convert the differentiable function as u. Because the derivative has to be, because the derivative of x would be 1. So that's not u. So u had to be ln x. The derivative of ln x is 1 over u. Okay, that does it for that chapter. Or that section, I should say.